So in today's lesson, we're going to continue our conversation about acids and bases and equilibrium. And so we're going to start to look at what are referred to as acid and base ionization constants. Sometimes we can abbreviate that to Ka and Kb respectively. We're going to start today by talking about Ka, but before we get into that, I just want to juxtapose strong acids and weak acids for you and how we go about calculating pH. Now, it all comes down to how we are able to differentiate between a strong acid and a weak acid. You'll remember that strong acids will dissociate 100%, right? So we'll see 100% dissociation in a strong acid, whereas usually we'll typically see, less than 50% dissociation in a weak acid. So that has some implications when we calculate pH. So generally speaking, we know that pH, we can calculate that by taking the negative log of our hydronium ion concentration, right? So that's easy to do. That's an easy calculation if we're looking at a strong acid, because if we have, let's say for example, our strong acid is going to react with water to produce our hydronium ion and the conjugate base, then we know that if we started with 100 molecules, say for instance of HA, then we automatically have 100 molecules of H3O+, which essentially means that, well, why does that matter? It matters because if we know the initial concentration of our acid, then that will also tell us the concentration of our hydronium ion in solution. That's easy. However, if we have the same situation, if we look at the same situation with our weak acid, we have our weak acid reacting with water, and it's going to produce hydronium as well. No big difference here. But the difference lies in the fact that if I were to start with 100 molecules of my weak acid, I'm going to have less than 50% dissociation. So in other words, less than 50 of my molecules would necessarily be not present in solution, right? So I would have, so in other words, when I'm going about calculating my pH, I can't really assume that my concentration of my acid is the same as my concentration of hydronium. And that's a problem, and that means that we need to look at the amount at equilibrium of hydronium that is present by looking at equilibrium calculations and ice boxes and things of that sort. So let me introduce you to this thing called the acid ionization constant, finally. So we can discuss the relative strengths of acids by looking at its acid ionization constant, which we know as, in short form, as Ka. So if we look at a generic acid dissociation according to the Bronsted-Lowry definition, here we have HA, which is a typical symbol we'll use for a weak acid. We're going to see it donating a proton, right? Acids are proton donors, to the water to produce hydronium. And what we have over here would be the conjugate base of our weak acid. So we have our weak Bronsted acid. It's going to donate its proton to water and thereby produce HA, a conjugate base, along with our classic expected hydronium ion. So we can write what's called a Ka expression, or a Ka, like an equilibrium law, an analogous equilibrium law for acid ionization constants. And by doing that, we're going to look at same basic format, products over reactants. So I have my concentration of my hydronium times the concentration of my conjugate base divided by the concentration of my acid itself. And so if you're wondering why water is missing in this equation, that's because remember that water is a liquid, its concentration is unchanging, and so we're not going to incorporate it into that equilibrium expression. Okay, so strong acids, already talked about this, will dissociate at nearly 100%. What does that mean? What would we expect for the Ka value for a strong acid? We would expect it to be large, very large in fact. Conversely, a weak acid is not going to dissociate completely, and so that indicates that there's going to be a lower proportion of ions in solution. Solution is definitely favoring the reactants in these cases, and so we would say that the Ka value is small. So I've got a little bit of a picture here to kind of describe that and juxtapose these two in a visual form. So if we have our weak acid here, or a strong acid rather, and it dissociates, we would be seeing 100% of the particles in solution. Whereas over here, if we have a weak acid, we start out with a certain amount of that weak acid in terms of moles per liter, but only a small proportion would actually be present as ions in solution. And so the majority of that reactant is still present before the reverse reaction starts to occur. So in the back of your textbook, in the reference section, you'll find a table B5, which has the Ka and Kb values for common acids and weak bases, common acids and weak bases. So table 1, you'll notice, is labeled as monoprotic acid. I'm just going to plant the seed. I want you to think about what that might mean. So when I examine this chart, I want to, draw a correlation between these acids and their strength. So the smaller the Ka value, the weaker the acid. So if I were to look at the top end of this chart here, I would see that there are a number of acids that have no listed value for the Ka. That is because they are very strong acids. They have, and hence would have large Ka values. They would be dissociating. That reaction is going to completion. So we're not really concerned about, their Ka value as a measured value because it's so large. It's not really worth considering mathematically. And so if we were to conversely look at some, acid like hydrofluoric acid, we would need to be, if we were looking to calculate the pH of a hydrofluoric acid solution, we would need to be aware of both the initial concentration of hydrofluoric acid, but as well as its Ka value to help us to calculate that pH. And so we're going to look at some examples that are exactly like that today. And so a typical type of calculation you might be asked to do is to look to calculate the percent ionization. And so percent ionization describes the amount of hydronium in terms of moles per liter present in solution compared to the initial amount of acid. And so, why do we use percent ionization? People understand that, right? We have a solid frame of reference for the meaningfulness of values in percents. So here's a typical example, and I want you to think about it and maybe see if you can give it a try on your own. So here is the example. Calculate the percent ionization for propionic acid if a 0.050 mole per liter solution has a pH of 2.78. So pause the video, see what you can set up on your own, and then we'll take it up together. So before we do anything, I just want to quickly show you how the approach for a weak acid has to be different than that of a strong acid. And I'm going to do that by just highlighting that the concentration of my initial acid, my propionic acid, is 0.050 moles per liter. And so sort of on the side here, if I were to do a quick calculation for pH using that concentration, I would take the negative log of my let's just say that this were strong. I would say 0.050 moles per liter. I'm getting a pH value of 1.3. So there's no way that this acid is strong because the pH of the solution, were it dissociating 100%, would be 1.3. And it's not. It's 2.78. So that means that I have to do some other calculations here. So I'm going to go about doing that. So the first thing I like to do is to write out the dissociation, the ionization reaction for this acid. So I know that I have my propionic acid, HC3H5O2. And I always just hydrolyze it. I'll react it with water. And that's going to form, of course, as my acid donates a proton, my hydronium ion, H3O+, and then my anion formed, my conjugate base formed when my acid loses its proton. So C3H5O2 with a -1 charge. And so I know that I'm starting out with a concentration of 0.050 moles per liter of this. Now, stoichiometrically, right, I know that there's a 1:1 ratio between my acid and my hydronium. So, you know, how much acid could dissociate? Okay, possible, so I'm going to call this my possible max H3O+ concentration is 0.050 moles per liter. And that, you know, that's just using ratios. Okay, my mole ratio. Now, what I do know, however, is that I can calculate the actual H3O+ concentration. So I'm going to say actual H3O+ concentration is going to be equal to 10 to the negative pH, right? So I know that my pH is 2.78, so 10 to the negative 2.78. So going ahead and substituting that value into the formula in my calculator and calculating, I get a value for the hydronium ion concentration at that pH. And I'm going to write this out to 2 sig figs, 1.7 times 10 to the negative 3 moles per liter. But I'm keeping my unrounded value in my calculator. So let's look at this. So I could have dissociated that much, but I only dissociated that much in actuality, right? So I have one last step to do here. And so I'm just going to duplicate this slide. And now I'm simply going to finish off this question. And so, you know, the last thing I need to do is to calculate the percent. So this is my percent ionization, right? Remember that it's the acid concentration actual. So I'm going to say H3O+ actual divided by my H3O+ maximal times 100. And so I can substitute in those values. So I'm just going to do that for the sake of time. And so let me go ahead and do that. And so I've got my 1.7 times 10 to the negative 3 moles per liter divided by the possible 0.050 moles per liter times 100, and I'm getting around 3.3%. So that is that. Let's look at a second type of example that you might see, which is calculating Ka. Okay, so let's take a read through this question. It says formic acid is a monoprotic acid. In a 0.1 mole per liter solution of formic acid, the pH is 2.38 at 25 degrees Celsius. Calculate the Ka for formic acid. Okay, so if I'm calculating the Ka for formic acid, you know, I know that my Ka is going to be equal to my reactants over my product concentrations over my reactant concentrations. And so best for me to probably set up a reaction equation to be able to deduce that. So that's going to be my first step. So I'm going to write out HCHO2 plus H2O reacts to make. And again, it's that first hydrogen that's going to be donated, that first proton that's going to be donated to form my hydronium ion. So I'm going to end up with H3O plus and my conjugate base, CHO2 with a -1 charge. And so I am going to look at doing sort of a quasi-ice chart. I just find that that seems to organize me nicely. And so, you know, I'm going to remember that my water is in the liquid state, and so its concentration is unchanging. I'm going to start out with 0.100 moles per liter of my formic acid. It's going to decrease by a certain amount, which I'm going to call X. And so I have an expression here, 0.100 minus X. So looking at my hydronium ion concentration, initially I'm going to have none of that, right? It hasn't dissociated yet. And so likewise, my conjugate base is going to be present in 0 moles per liter, but they're both going to increase according to their mole ratios, which is X and X. Now, the difference is that in this question, I'm actually given pH. I'm given that the pH is 2.38. So that is actually helpful for me and will constitute what I would do next. So I'm going to call this step 2. And what I'm going to do is I'm going to calculate the pH. I'm going to use that pH rather to calculate my hydronium ion concentration. So the hydronium ion concentration is equal to 10 to the negative pH, as we just saw. So 10 to the negative 2.38 is going to give me a value, and essentially that value is going to give me the empty spot right here. So I'm going to go ahead and do that calculation. So if my calculator is correct, I have a value for my hydronium ion concentration of 4.2 times 10 to the negative 3 moles per liter. Okay, and so now I can go ahead and I can just simply substitute that in. 4.2 times 10 to the negative 3 moles per liter is actually, you know, that's my value for X. So because I know that, I'm going to be able to determine the concentration. You know, here's an expression for the concentration of my initial acid, my formic acid. You know, I know that this is going right here. I can complete my ice box, and that's going to give me X right here. And so this X is equal to that X. And essentially I'll have all values I'm going to need to calculate Ka. So the next thing I'm going to do, I'm going to call this step 3. It's going to write out that Ka expression. So Ka is going to be equal to the concentration of my H3O plus times the concentration of my CHO2 negative divided by the concentration of my acid, HCHO2 minus, O2 rather. And so I have values for each of these now. So I can substitute those in. So remember that my concentration of my acid was that 4.2 times 10 to the negative 3 moles per liter. Same goes for my anion, my conjugate base anion, 4.2 times 10 to the negative 3. And the expression I had over here for my for this initial acid was, you know, X minus, or sorry, rather 0.100 minus X. So that's actually just what I'm going to substitute in here. I'm going to put 0.100 minus 4.2 times 10 to the negative 3. Now I have everything I need. I just need to plug all these values into my calculator to get a value for Ka. So go ahead and do that. I'm going to do the same and then come back with a value for you. And so I am getting a value to 2 significant digits of 1.8 times 10 to the negative 4 moles per liter. No units. My mistake there. No units. All right. So hopefully you did okay with that. We're going to carry on to the next question. So in this example, we're going to be calculating the hydrogen ion or hydronium ion concentration for a weak acid. And so typically here we're going to be given some information about the acid, but we're going to need to research a Ka value. So let me break this down for you. It reads, the concentration of a sample of vinegar was found to be 0.75 moles per liter acetic acid. And that's what vinegar is, acetic or ethanoic acid. Calculate the values for your hydronium ion concentration and your pH for this sample. So again, since I know that vinegar or acetic acid, ethanoic acid, if you will, it's a weak acid, I know that if I were to simply do my pH calculation here by taking the negative log of my 0.75, that would give me a value that is not actually the pH of the solution. I can't really go about that. So that means that I'm going to need to use some equilibrium knowledge of equilibrium and equilibrium calculations. So that's what I'm going to do. So I would like for you to pause the video and try a couple of things, and then come back when you think you're ready to get started. Okay, so what I would do in a question like this is I would first start by writing out the relevant reaction. That would be my step number one. And so I'm going to go about that. So I start out with acetic acid, HC2H3O2. I'm going to add it to water. And of course, this will be aqueous. This is a liquid. And then I'm going to dissociate it. And so that's going to form my hydronium ion concentration because this acid, again, is going to donate a proton. It's a proton donor. And that's going to give me my acetate ion, C2H3O2 with a -1. And I believe that your textbook actually shows acetic acid as ethanoic acid, but I could be wrong. And so I'm going to set up an ice chart here. Ice. And I'm going to remember that since water is a liquid, its concentration is unchanging. And now I'm going to start to fill in some data. So I'm starting with, an acid concentration of 0.75 moles per liter. And I'm starting off with initially no ions present in solution in any concentration. But I know that the amount of my acetic acid is going to go down. And that gives me an expression of 0.75 minus X at equilibrium. And so, likewise, the ion concentrations are going to increase in conjunction with their mole ratios. And since the mole ratios are 1 and 1, respectively, I have some lovely expressions for all of my equilibrium concentrations. So that's my first step. Now, the next step that I would take is I'd go about and take a look to see if I can find the Ka value for my acid. So I am going to just scroll up here. Here's ethanoic acid, and it's 1.8 times 10 to the -5. So I'm going to go back to my chart, my question, and I'm going to make sure that I acknowledge somewhere in the problem, because, if you're not sure where to go next, it's always good to have some information written down. I would write out that that the Ka value, you knew to look that up as an important piece of data. So 1.8 times 10 to the -5. So, I need to know those things. And so hopefully you're thinking about what it is that you should be doing next. And what you should be doing next is writing out some sort of a Ka expression. So I've moved to another slide here, and I'm going to call this step 3. And I'm going to write out a Ka expression for this question. So Ka is going to be equal to the hydronium ion concentration times the concentration of my acetate ion divided by the concentration of my acid at equilibrium, C2H3O2. My ethanoic acid. So substituting in my value of 1.8 times 10 to the -5 for my Ka value that I just looked up. I'm going to say that my H3O plus concentration was X, and so is my acetate ion concentration. And I have 0.75 minus X as my expression for my acid at equilibrium. Okay, so now here's where we have to have that special talk about simplifying our math. Now I notice here that I have a value of X here. And so that value of X is going to, if I were to solve this, I would bring this whole expression up, distribute the 1.8 times 10 to the negative 5 and end up with a quadratic. But the reality is that this right here, this X that's being, this small little tiny amount that's being, subtracted from my initial acid molarity is going to be very, very small. And so what I'm going to do then as a result is I'm going to be able to simplify my math and get rid of that X entirely to create a more simple mathematical expression. And so that's what I'm going to do. Let me just go ahead and do that. So I'm rewriting this. 1.8 times 10 to the negative 5 is equal to X squared over 0.75. And now what I have is an equation that's quite simple to solve. I'm going to isolate my X in the next couple of steps here. So I have 1.8 times 10 to the negative 5 times 0.75 is equal to X squared. And so that's an easy enough, by taking the square roots of each side, I can easily enough solve for my X, and I'm going to go ahead and do that. So that's giving me a value to two significant digits of 3.7 times 10 to the negative 3, and that's the unit of moles per liter. Now remember, when I go back, I'm just going to switch back to the last slide here, that the value, what did X actually represent? Well, X was an expression we used to represent the equilibrium concentration of hydronium. And I was asked to find the pH of the solution and the hydronium ion concentration. So far, I have accomplished one of those tasks. I can say that my hydronium ion concentration is equal to X, so therefore that is my hydronium ion concentration. Once I know that, my final step is going to be, I'm going to call this step 4, is to actually calculate the pH of the solution. So pH is equal to the negative log of my hydronium ion concentration, which in this case is what we just found, 3.7 times 10 to the negative 3. And so you probably still have that value in your calculator. So I would just press log and then negative, and that will give you a pH of 2.43. So hopefully you found that question to be not too bad. Just that extra step at the end, again, to find your pH, and remembering that initial concentration cannot be used to find pH because this is a weak acid that's not dissociating 100%. So that brings us to the end of our first part of the lesson on acid and base ionization constants. Remember, as always, if you're struggling with this, to reach out, and I'll do my best to support you in your learning. That can best be done by email. So just reach out and I'll see what we can do.